Hello and welcome back. So far we understood how logistic regression algorithm works, or how exactly it gives you the decision scores or the probabilities. Based on probabilities and decision scores, how can we actually play with the model and get the performance, the precision or recall scores we want. But we haven't understood how exactly the thetas are found or the pattern is recognized. In logistic regression, in the first slide, I showed you that the function learns these thetas. When you feed the train set, the algorithm learns these thetas. So how is it going to learn? What is the solver behind it? You can use normal equation or gradient descent. Let us try to understand gradient descent and how it works and how it finds thetas. So for gradient descent, the cost function is the basis, right? I hope you remember. In linear regression, it took squared loss function because it is convex, and it started taking a random thetas and then started moving those random thetas towards the global minimal error place. I hope you remember that. So the same concept applies here also, but the cost function is going to be different. In logistic regression setup, if you try to use squared loss, h of x minus y whole square, the h of x is equal to 1 by 1 plus e power minus z. Z is nothing but theta transpose x, or the linear combination of all input values. So this is going to be non-convex. So when a non-convex function is taken as cost function, the gradient descent algorithm fails to find the global minimal theta. It may actually get stuck at one of the local minimas, or it may not actually reach to the global minimal place. So we are going to take the log loss function as mentioned here is minus y log h of x minus 1 minus y log 1 minus h of x. This is the function. This is actually a cross entropy function. We will understand cross entropy function when we understand softmax regression classifier. For now, just take this as log loss function minus y log h of x minus 1 minus y log h of x. This is a convex function. Why this is a convex function? Let us see. If you look at log x, the curve is going to be like this. If you take minus log x, it's going to be like this. If you take log 1 minus x, the curve is going to be like this. If you apply minus in front of it, it's going to be like this. So when you combine the minus log x minus 1 minus log x, it becomes a convex function like this. So the same technique is applied here on the logistic regression also. The cost function j of theta is equal to minus y log h of x minus 1 minus y log 1 minus h of x. H of x is 1 by 1 plus e power minus z. Z or z is equal to linear combination of theta transpose x. Right? So the cost function is convex. So the gradient descent algorithm can actually converge to global minimal theta. So it chooses some random theta and calculates the slope and subtracts the slope from the current theta by multiplying with the learning rate. So that's how the gradient descent algorithm works. So the cost function for positive record and cost function for negative record are these two terms. This term minus y log h of x is cost function for positive term. Minus 1 minus y log 1 minus h of x is a cost function for the negative term, right? Because if you try to substitute 1 here, this term becomes 0. If you see this minus y log h of x minus 1 minus 1, this whole thing becomes 0. So it is minus log h of x. This is a cost function for positive record. And if you put y is equal to 0, this term becomes 0 and the other term remains. So minus log 1 minus h of x is the cost function for negative record. When you combine these two and we created a common function which is convex for both positive and negative records. So how gradient descent algorithm works, let us see. The gradient descent formula is theta 1 is equal to theta 1 minus alpha into derivative of cost function with respect to theta 1. Here I have taken W1, that's okay. Weight, right? It's a weight. And here I took B. Instead of B, you can take theta 0 or theta 1, right? But the gradient descent algorithm is this part, W1 minus alpha is the learning rate into derivative of the cost function with respect to theta. Why this is? The W and B are chosen randomly initially and then they get adjusted so that it moves to the global minimal place and becomes the perfect decision boundary. In logistic regression or classification, we call the line as decision boundary. In regression, we call it as best fit line. So to calculate the derivative of cost function with respect to W or W1, we need to apply chain rule, because between W and the cost function there are two more functions. We are trying to identify the rate at which the cost is changing when you change 1 unit in W. That is derivative of cost function with respect to W1. When you change W1, first Z will change, Z will change. When you change Z, the A will change. When you change A, J will change. So we need to multiply the changes to find out the total change. When you actually change 1 unit in W1, how much change is happening in J. So when you change W1, Z will change. That can be found by dZ by dW1. When you change Z, or when Z changes, Z changes, A will change. dA by dZ can find that. And when A changes, J will change. That can be found by dJ by dA. And when you multiply all these three and multiply with alpha and subtract it from W, it moves one step in the gradient descent. So this is called as back propagation. Frankly speaking, in back propagation, nothing going backward. Calculating this derivative or using chain rule and calculating this derivative is called as back propagation. I don't know why, but it is called as back propagation. So we are adjusting W, right? To calculate, to go forward, we call it as forward propagation. You take random W and X, random B and X0, multiply these and add them, linear combination you find out, and substitute into logistic function, and then find out cost. It is called as forward propagation. We need to adjust W to do next forward propagation. To adjust it, we'll use chain rule and find out the three derivatives, multiply them and subtract from W by multiplying with alpha to control the step size, and then find next W and next B. If you see the next B also, B is equal to B minus alpha into dJ by dB. If you look at these two terms, dA by dZ and dJ by dA are common for both W and B. Once calculated, can be used throughout the network. So, to do the next forward propagation, you found the next W by substituting this dJ by dW1, right? And you found dJ by dB and substituted it, and you found next B. You multiply it, again you calculate linear combination, again you find A, again you find J, and this whole process happens until the cost becomes minimal. In a logistic regression setup, the cost function is convex, and there is a place where the slope of the tangent or the derivative of cost function with respect to W1 is 0, or derivative of cost function with respect to B is 0. You do n number of epochs to reach to that place. Same logic applies. We have understood gradient descent algorithm in linear regression. If you forget it, just go back and look at the video one more time. The same logic applies here also. The formula changed. More derivatives got added to calculate next W, that is called as back propagation, because of there are more functions between the cost and the W. In our linear regression setup, the cost function can be expressed in W's or can be expressed in thetas. So we actually did derivative directly. Here it is not possible because there are many functions in between. So the same logic applies in deep learning also. We'll cover that there. So this is how logistic regression is finding thetas. Thank you.